So we had this strange behavior of light that you always get the same speed when you measure the speed of light in a vacuum. You always get the same answer. Why? So along came Albert Einstein. He offered the following explanation. First of all, he began with two postulates. A postulate is, I'm not going to prove this. I'm going to assume it's true and see where it goes. So his first postulate is, if two frames of reference move with constant velocity, if you're moving at a constant velocity, what's your acceleration exactly? So A is 0 relative to each other. Then the laws of physics will be the same in both frames of reference. What? Here's what he's saying. Let's suppose you're sitting right now at your desk and sipping on instead of a thick beverage, let's make it a cup of coffee where it's almost filled to the top. Okay? If you're in a perfectly smooth car going at a constant speed, the coffee will not slosh. It will only slosh when I'm looking for a word that starts with letter A. So he already started to say, nice, yeah, Aiden, we heard that. So already Einstein was thinking acceleration is weird because it changes the laws of physics. But constant velocity, he said, I'm going to assume that the laws of physics don't change whether you're at rest or at a constant velocity, or if two objects are traveling at constant velocities different from each other, they will still experience the same laws of physics. I think that's reasonable. In other words, if you pour a cup of coffee while on a jet plane that's traveling at 700 kilometers per hour, the coffee pours straight down. It doesn't kind of arc backwards as you're pouring it. It would only do that if there was, I'm looking for a word that starts with letter A, Aiden, acceleration. Okay?
Yeah, I got that.
You can try this yourself if you're not driving a car. Play catch when you're in a car. If you're at a constant speed, if you throw something up, it'll come straight back down. It won't end up in the back seat, even though the car is moving forwards. And the reason is both you and whatever you're playing catch with are at the same relative velocity. Okay? Now, here is Einstein's thought experiment. I want you to imagine a van that has one whole side made of glass so that you can see inside of it. And I'd like you to imagine that there's somebody in the van playing catch, except instead of the ball traveling sideways like in this picture, they're going to throw the ball straight up and have it come straight back down. That's what they see. What would you see? So here's the van as it's driving in this direction. I think you would see the ball travel like this. Now I get rid of the van because really inside the van they would see the ball going like that, but an observer on the side of the road would see something very different. Yeah. I'm ignoring that. I just want to look at the moving object right now. I know everything's moving, but I want to look at the ball. Remember that. The second postulate, Einstein said, okay, I'm going to accept the results of the Michelson-Morley experiment. The speed of light in space will be the same for any observer, no matter what the velocity of the observer's frame of reference is, and no matter what the velocity of the source of light is. In other words, I'm going to accept that the speed of light is a constant. This leads us to time dilation. Note, dilate means to make wider or longer. So when we talk about time dilation, we're talking about the slowing down of time for one object relative to another object. According to Einstein's special theory of relativity, a clock that is moving will slow down. A moving clock will run slower. The stretching of time by a moving clock is called time dilation. And Max, this is why I said, let's ignore the person in the van. We're going to replace the ball. Since light is what's behaving weirdly, let's replace the ball with a beam of light. And let's have it bounce off of a mirror so that it's just bouncing back and forth, back and forth, back and forth. But let's only do it once. Let's have it bounce straight up and come straight back down inside the van. Better yet, let's make it a spaceship so we can go faster. But a transparent spaceship, we're going to imagine that we're astronauts in our spacesuits floating at rest in space, watching the spaceship zoom by. And we're going to have to imagine that we have Superman eyes because the spaceship's going to go really fast, but we're going to pretend that we can see what's moving. Okay? Einstein was famous for thought experiments, so this is what we call a thought experiment. We're going to have the spaceship travel forward at a speed v. It's not going to accelerate. It's going to be a steady speed relative to the observer. Okay. Is it possible that in two different frames of reference, identical clocks might run differently and that time might pass differently? Yes, this is one of the predictions of Einstein's special theory of relativity. Special relativity, A is 0. Einstein already said, look, I know that when we stop or speed up, the coffee cup sloshes. That's a different law of physics. Something weird's going on there. I don't know how to deal with that yet. But for now, I'll start out with, what if we're moving at a constant speed? I always say it shouldn't be called special relativity. It should be called special case relativity. What's the special case? A is 0. General relativity should be called general case relativity. What's the general case? Oh, now you can speed up and slow down. Accelerate. So figure 15.6 illustrates our upcoming thought experiment. We have a special custom-made glass-walled spaceship, and it's made so that an outside observer who's floating in a spacesuit can watch an experiment done inside by an inside observer. The inside observer is watching an event consisting of an imaginary oscillating light beam, a light beam going up and bouncing back down. Put your pencils down, look up. Let's run with that. Next page. The oscillating light beam acts like a clock. Each, quote, tick is up and back down. The beam goes from the source up to mirror A and back to mirror B. The inside observer measures the time for the light to travel from A to B, and let's pretend that the inside observer finds the time to be, we're going to call it T0. They figured out that they'd left something here. Figured they would. T0, I always think of T0 as time TO, time on board the spaceship. That's how I'm going to remember that. This is time on board the spaceship. And since distance equals speed times time, the distance the inside observer sees the light beam travel is speed of light times time, c times T0. This is the Einstein derivation that I'm going to walk through. Okay? So this distance right here, don't write this down, would be speed times time, because d equals v times t. Oh, because a is 0. Don't write that down, Deegan. We're going to do a better diagram. Okay? Now, this is what we see the light travel. So we're going to measure how long that takes on our stopwatch. And then its distance will be speed of light times our time. T0, time on board the spaceship. T, our time at rest. And then the last thing, this distance here is the speed of the spaceship times our time, because that's how long we've measured the spaceship to be traveling. See the triangle? I told you that Einstein proved his paper with Math 8. We're going to pull out Pythagoras, Math 8. Okay? So we're going to DULP. DULP stands for draw a little picture. We're going to draw a triangle, make it a right triangle. Each of these sides is going to be a distance. The vertical side distance was that. And what we're using, if you want to, you can write at the top of the page, we're just constantly using the fact that distance is speed times time. If it's a light beam, the speed is going to be c. But we're going to have to talk about which time is being measured by whom. So this is on board the spaceship, so that's the time on board the spaceship. This is speed times the time we measure, speed of light times the time we measure. Because we see the light beam travel like that. Remember the video I just showed you? We saw the little V shape. And then this bottom is the actual spaceship traveling. The spaceship is traveling at a speed v times our time, because we are the ones watching the spaceship. Who remembers what's Pythagoras? Max, loud and proud. Where this is going to be A, that's going to be B, that's going to be C. I realize we have two different C's that mean different things, so don't freak out. This is the equation that Einstein generated. We're going to say, okay, C times T0 squared plus V times T all squared has to equal C times T all squared. It's complicated, but Owen, I'm going to argue it's Pythagoras. Ugly Pythagoras, yes, but Pythagoras. Next step is we're going to get the CT0 squared by itself. How would I get this by itself? I guess I need to move this over. How? Okay, so we're going to write this as, in brackets, CT0 all squared equals CT all squared minus VT all squared. The next step we're going to do is distribute the powers. And what I mean by that is we're going to put the squared onto there, onto there, onto there, onto there, onto there, and onto there. We're going to get rid of the brackets. So that's going to give us little c squared, T0 squared equals little c squared T squared minus V squared T squared. Still technically Math 8. Complicated Math 8, yes. Still technically Math 8. Ethan, what's it say for step 4? What does it want us to do? Divide this by c squared, this by c squared, and this by c squared. Is that allowed? Did we divide everything by c squared? Then we're still following our equation solving rules. Now, what's kind of nice is here, those c squareds will cancel. Yay. Here, those c squareds will cancel. And we'll end up with T0 squared equals T squared minus V squared T squared over C squared. Camille, what's it say for step 5? Can you see there's a t squared there? And is there a t squared there? GCF. Okay. So I can write this as T0 squared equals, factor out a t squared bracket. When I factor out a t squared out of a t squared, what's left behind? Not a 0. Yes. And when I factor this t squared out, I think I'll just have left. Next page. We want to get the t by itself. First of all, I'm going to get the t squared by itself. I'll stay on this page so you can all look up. What's this bracket doing to the t squared? So I'll get this. T0 squared over 1 minus v squared over c squared equals t squared equals t what? Equals t what? What? So my final step, I'll square root this side. Look up, keep watching for a second. I'll square root the top, and I'll have to just square root the whole bottom because I don't have everything squared down there, so I can't just do that. This is the time dilation equation. It says this. T equals T0 all over the square root of 1 minus. I'm going to change how I write it a tiny bit. I'm going to write it as V over C all squared, and you'll see why in just a bit. If you look on the back page of your green sheet, about halfway down, you should see the time dilation equation. So my first question is, do you need to memorize it? But you need to know where it is on your sheet, and I'll show you how we use it. So you absolutely want to get your calculators out, because this is about as complicated a calculator work as we're going to do. Now let's talk about what all of these mean. This is the part that you will need to memorize. And so this box you want to make a little note of. T is time for the object that's at rest. And you can put in brackets, it will usually be good old Earth. T0 is time on board the moving object, spaceship, let's say. And I remember T0 as time on board. I think of it as an O. V is the speed of the moving object, how fast the spaceship is traveling relative to the Earth. And who remembers what little c was an abbrev for? Light. Speed of light. Okay. So, example 1. Here is a classic time dilation puzzle. Spaceship is traveling at 85% of the speed of light. If 1 year passes on the spaceship, how much time passes back on the Earth? Since this is a new equation, let's go back to our DFIC approach. What's this question asking me to find? How much what? Keep reading. Is that T or T0? Okay. That must mean they told us T0, the time on board the spaceship. How much time passed on board the spaceship? And one of the nice things about Einstein's equations is they are unit independent. As long as you put everything in the same units, they'll work. If you want to put all the times in hours, that's fine. If you want to do all the times in seconds, that's fine. If you want to do all that, but as long as all your units match, it doesn't matter what units you put in there, as long as you're never putting hours and seconds into the same equation, or kilometers and meters. Whatever units you're given, as long as they match, use those. All right? Everybody underline this. 85% of the speed of light. That is V. The question is, how are we going to write that? Well, first of all, we never do math with a percent. We always change it back to a decimal. So 85%, put your calculator down, George. 85%, what's that in your head as a decimal? What word appears right after the percent symbol? What single word appears right after the percent symbol? It has 2 letters and starts with an O. What does of mean in math? In other words, when I say 5 and 6, that usually means add. What does of mean? Yes. Means of means times. The only time it doesn't is if it's contained in the phrase to the power of 6. Then it means an exponent. Everywhere else, anytime you see the word of, means multiply. Okay? Speed of light. We have a symbol for that. That is how I write 85% of the speed of light. Now let's write out our time dilation equation. T equals T0 all over the square root of 1 minus, in brackets, V over C all squared. Deegan, what were we trying to find? First of all, for this unit, don't say time, either say T or T0, because that's going to be important. What are we trying to find, T or T0? T. Do we have the T by itself already? Oh, okay. Plug and chug. Deegan, what's time on board the spaceship? No, what's time on board the spaceship? Thank you. Put your calculator down, Max. Okay, hold off on the calculators for a second. And then it's going to look like this. 1 minus, Deegan, what's V? No, thank you. Over C, all squared. Do you see? Do you see? Do you see? What do you see? We can cancel out the C's, which is why I wrote it this way inside the brackets instead of having the squareds on there. Do you see? Do you see? Do you see? Bad joke, but you're going to hear me say that every time. So now I'll get my calculator out. How will I type this? I'm going to show you a method that I know will work for all of you, and then I'll let you find, those of you that have the fancy schmancy fraction button can take shortcuts. But for now, bed mass. A square root comes under E for exponent. We do it first. So all of you go like this. 0.85 squared and hit equals. That's the brackets inside. 1 minus that. So 1 minus answer button, hit equals. Should have 0.2775. Square root of that and hit equals. That's the bottom of this fraction. Deegan, what's on the top? 1 divided by answer button. 1 year on the spaceship will be basically 1.9 years, almost 2 years back home on Earth. So if this spaceship went out for 6 months and came back for 6 months, on the spaceship 1 year would have gone by, but they would arrive almost 2 years in the future, not 1 year in the future. By the way, the proper abbreviation for years is a lowercase a for annually, because a lowercase y is yards. So I'll write that. If you put a y, I'm not taking marks off, but you know I'm enough of a nerd that I just have to do it right. Okay? Yeah? Now it gets weird. Example 2. Imagine your age is 30 years and you have a daughter who is 5 years old. You leave on a spaceship in the year 2000. I'm starting in the year 2000 because that way we can do the math in our heads. And you travel at a speed of 0.99 c, or what percent of the speed of light? For a time of 6 years as measured by you and the spaceship. So you're going to go out for 3 years, turn around, come back for 3 years, 6 years. In other words, from the space traveler's frame of reference, T0 is what? 6. Time on board the spaceship. How much time will have elapsed when you return on the Earth? From the frame of reference of your young daughter who was left behind on the Earth. Use the time dilation formula. What's this question asking me to find? T, not T0. And by the way, the tricky part is, are they asking me to find T or T0? And it's a lot of plug and chug on your calculator, but I think we can handle that part. So that means, George, they told me time on board the spaceship. What? What's V?
0.9x.
You all see the time dilation equation on your green sheet? What are we asked to find? T or T0?
T.
Is the T by itself on the time dilation? Oh, okay, so let's write it down. Put your calculator down, Max. One minus V over C all squared. As you get good, I'll let you take shortcuts, Max, but right now there's enough room to make silly mistakes that I'm being very fussy. We can plug and chug. 6 divided by square root of 1 minus 0.99C over C all squared. Do you see? Do you see? Do you see? What do you see? Well, that's convenient. So now you can pick up your calculator. If you want to try this on your own with shortcuts, you can. If you want to follow along with me, I would go like this. 0.99 squared. 1 minus that. Square root of that. 1 divide, oh, not 1 divided by, 6 divided by that. No. 42.5 is what you should get. Okay? So here's what this means. Having left the Earth in the year 2000, you'll return to Earth in the year 2042. How old will your daughter be? She started out 5 plus 42.5. She'll be 47.5 years old. How old will you be? You left at age 30. How long were you gone for? This is how the universe works. You will arrive back younger than your own child. No, that's the universe. Okay? This is why you'll often hear me say, if we do ever develop spaceships that can go near the speed of light, they're going to be one-way trips because like you'll either take your whole family with you, okay? Because would you want to come back younger than your child, having missed most of their life, and oh, just for giggles, you'll probably watch them die before you do. Probably not anyone's first recommended choice. So it's going to be what we call generational ships, where you're taking an entire family and maybe even having kids while you're out there and they're having kids, or you're just not going to come back. You're going to cut your ties. It'll be people that don't have kids and don't have many ties. Yeah.
Did you answer the other question?
I'm still thinking about it. Okay. This is how our universe works. So is time travel possible? This astronaut would have traveled 42 years into Earth's future. Absolutely time travel, totally doable. Put your pencils down, look up. Next page. So I think I should have said I like number 1, I like number 1, example 1, I like example 1, I like example 3, I like example 3, I like example 3. I like example 2, but I've already done the parent-child. I might do the parent-child one. I like all these, sure. Suppose a spaceship is traveling away from the Earth at 99.9% of the speed of light. It wants to arrive back on the Earth 1,000 years in the future. How many years will it need to be traveling for? How many years elapse for those on the spaceship? What's this question asking me to find? Sorry? T0. Time on board. Is that okay, Ethan? Can you all look at the time dilation equation on your green sheet? How would you get the T0 by itself? What's that square root doing to the T0? So are you telling me that T0 is t times the square root of 1 minus v over c all squared?
Yes, I am.
Yep. I think it's fair for me to ask you to derive that one. So let's make our list up here. What's t? Time back on the Earth? 1,000. What's v? 0.999 c. Don't forget the c. So it's going to look like this. T0 on board the spaceship is going to be 1,000 square root of 1 minus 0.999 c over c all squared. Do you see? Do you see? Do you see? What do you see?
So,
The c cancels. How would I type this in? Again, you can play around with your calculators and find the shortcuts, but on a basic level, I would probably go like this: 0.999 squared, 1 minus that, square root of that, times 1,000. And I get 44.7. Is that right? So if they went out for 22.35 years, turned around, came back for 22.35 years, that would be, for them, 44.7 years, and they would arrive in the year 3020. So again, is time travel possible into the future? Totally. Hello, hello, hello.
What I'm walking into.
There you go. Absolutely. Max asked, how do we do time travel into the past? I'll show you maybe a theory that might work. That's preview of coming attractions. But for now, we really need to think about the implications. So already, time is not the same for two objects if one is moving relative to the other. But there are some weird consequences, because if distance equals speed times time, or if speed equals distance times time, I told you if you're always getting the same answer for the speed of light, there must be something weird going on with time. There's also something weird going on with space, with distance. I like example 4. I like example 4. Example 4 is a nice question. Proxima Centauri is the closest star to the Earth. It's 4.24 light years away. A light year is not a measure of time, it's a measure of distance. It's how far light would travel in a year. So, A, suppose we build a spaceship that can travel at 80% of the speed of light. How long will the spaceship take to get there as measured by stationary observers on the Earth? So we're going to start out with the Earth stationary. This is not a relativity question. This is us just doing the calculations at rest. We're not going to bring in relativity here. We're just going to say, you know what? This wants me to find time when my distance is 4.24 light years. Oh, wait a minute. I got an abbrev for the speed of light. CA, that's my abbreviation for light years. And the speed we're going to travel is 0.8 c. And the reason right now I'm not using relativity is right now we want to see what's going on at the Earth at rest. I don't know how much time will elapse on the spaceship. What we're really technically finding is time back on Earth, just with straight d, v, and t. You know what? Why didn't I write VIT plus a half AT squared? I said for this unit, A is going to be what? Einstein didn't know how to deal with that yet. Deegan, how would I get the T by itself? By? Yep. The time that we're going to estimate that this mission is going to take for us back home on Earth, Pinel, is D over V. By the way, I want you to notice we have 4.24 light years divided by 0.8 c. Do you see? Do you see? Do you see? What do you see? Again, Yay! So if we are budgeting how long NASA has to man the controls for this mission back home on Earth, how long we have to staff the control room, what do you get? 4.24 divided by 0.8. 4.24 divided by 0.8. 5.3 years. So as far as we're concerned, they're going to arrive at the star 5.3 years from us right now. Now, B, how long will it take to get there as measured by the observers on the spaceship? What's this question asking me to find? T0. Well, V is 0.8 C. What's T? What? That's why I had to do that little calculation first. 5.3 years for us. What's the T0 equation? Is it times by the square root or divide by the square root? Times? So T0 is going to be T times the square root of 1 minus V over C all squared. It's going to be 5.3 times the square root of 1 minus 0.8 C all over C squared. Do you see? Do you see? Do you see? What do you see? So it's going to be, if you want to type this in one step, you would go 5.3 times square root button bracket, or if you have one of the newer calculators, it might put the square root thing in a bracket for you automatically. 1 minus 0.8 squared close bracket. So I can get there in one step. This is what you can kind of play around with on your calculator and see how it works. On the spaceship, Max, as far as we're concerned, 3.18 years will have elapsed. I'm okay with that because, Annika, we said time moves slower, clocks run slower on a moving object. Less time passed on the spaceship because it's moving relative to the Earth. I'm okay with that. But here's where it gets weird. What's the distance traveled according to the observers on the spaceship? Suppose the spaceship trailed behind it a cosmic tape measure, a massive, long tape measure. How far will it have traveled? Well, distance equals speed times time. Although, since it's the spaceship, yes, times 0. What speed is the spaceship traveling? 0.8 C. How much time? Hey, do you notice we're going to get light years as our answer? That's kind of cool. So from the Earth, we measured Proxima Centauri to be 4.24 light years away. Now we send a spaceship to actually measure the distance, and the spaceship measures the distance to be not 3.54 light years away, 2.54 light years away. Ready? If the spaceship traveled faster, this time here would be even smaller. This result would be even smaller. Not only is it impossible to say how time is passing relative from one to another, it's going to be different. It's impossible to measure distances in outer space because as soon as you start to travel there, the distance that you measured when you were at rest will change. How? Space-time itself is compressing in the direction that you're traveling. Let me say that again. As soon as you start to travel in your spaceship, the distance that you'll travel will be a different physical distance than the Earth actually measured. The Earth's messages via radio will travel a different distance to get to the same star that you have traveled with your spaceship. It gets weirder, but cooler, but weirder, but cooler. Example 5. How much time passes if you're traveling at the speed of light? Okay. Well, if you're traveling at the speed of light, if you're on board the spaceship, I guess we would want the time on board equation, which is the square root of t minus 1 over v over c all squared. I don't know what t is, but if we're traveling at the speed of light, what's v? Yeah. So I'm going to get this, Annika. I still don't know what t is, but it's going to be the square root of 1 minus c over c all squared. Do you see? Do you see? Do you see? What do you see? When we go c divided by c, when they cancel, what number is left behind? C divided by c is 0? What? What? So cross this out, replace it with a 1. Put your calculator down, Owen. Owen, what's 1 squared in your head? What's 1 times 1? What's 1 minus 1? What's the square root of 0? 0. What's 0 times anything? How much time elapses if you're traveling at the speed of light? Time does not exist. It gets weirder, but cooler, but weirder, but cooler. Here's what that means. Even though we like to look up late at night, and when we see the stars traveling, when we see the stars out late at night, we like to say it took the light from those stars thousands of years to reach us, or millions of years to reach us. As far as those photons were concerned, the trip was instant. They left, they arrived. Because they don't experience time. Even though, for our stationary reference frame on Earth, we say that it can take light from stars thousands or millions of years to reach us, in actual fact, relative to the beam of light, if those photons could think, how much time has passed? It gets weirder, but cooler, but weirder, but cooler. Because light beams don't experience time, look up. For those of you on YouTube, I have just turned on my camera flash. Do you see photons leaving from it? What do those photons experience? Because those photons don't experience time, right now, simultaneously, they are seeing the Big Bang and the end of the universe. They are witnessing that. They don't experience time, which means they're in all times at once. Time is not a thing for a photon. Any photon has been around since the beginning of the Big Bang as far as it's concerned, and simultaneously it's watching the universe end as far as it's concerned. Light is special. I wasn't kidding when I said light is special. Light is special. Preview of next lesson, it's going to get weirder, but cooler. No, there's no time is irrelevant. To say that you could see the future would suggest that you could view or narrow in on a specific time. Doesn't exist for beam of light. Okay? Example 6, a spaceship is traveling at 2.85 times... I like example 6. I like example 6. Example 6 is a nice question. A spaceship is traveling at 2.85 times 10 to the 8th meters per second. Leaves the Earth, returns to the Earth 100 years later. So goes out for 50 years, turns around, comes back 50 years, 100 years. How much time has passed for those living on the spaceship? What's this question asking me to find? What's T? What's V? This time I didn't give it to you as a percentage. I gave it to you as an actual number. It's 2.85 times 10 to the 8th, which means, sadly, this time, do you see, put your calculator down, George, do you see is not going to work. But we'll have a workaround. What are we finding? The T0 equation, is it times the square root or divide? I can never remember. Is it times? So it's going to be T times the square root of 1 minus V over C all squared. So it's going to look like this. 100 square root of 1 minus, what's V this time as a number? 2.85 times 10 to the 8th. And then look up for a second, please. Don't write this down. Do you see does not cancel? Instead, I have to put in the number for C. What's that? It's on your green sheet. I think it's right by the relativity stuff. Pretty sure I told you what C was. So I'm going to have to put a 3 times 10 to the 8th in. Yeah.
Where did we get 3 times 10 to the 8th?
Like, you mean,
Like, how do we know it's 3 times 10 to the 8th?
we've measured it. Sorry. I just lied. We've both measured it, and technically we haven't ever measured it because technically it's impossible for us to measure it.
We haven't measured it, it's just the best guess.
Hold that. I have a video that will go into the... First of all, we've sort of measured it. I'll say it this way. We have yet to come up with an experiment that has disproved this value. That I can say. Okay? Which isn't the same as me saying we've measured it. I'm saying no experiment that we've been able to come up with has disproved this. And it's been used over and over and over, and we get results that work. Okay. No. It's far weirder than you realize, but cooler. Okay? No, so the speed of light is actually 2.9979 something, 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 and it's exact. It's one of the few values that's exact, but the reason it's exact, Aiden, is we defined it that way. And then we've adjusted all of our other units to match that value. But it's weirder than that. Look up. I would do inside the brackets first, so it's going to be 2.85 scientific notation button 8 divided by 3 scientific notation button 8 equals, oh, I forgot the squared, and that's a common mistake. Don't forget the squared. I wish I'd done that on purpose. That would be good teaching. So squared, 1 minus that, square root, answer button, times 100. How much time will elapse on the spaceship? 31.2 years. So as far as I'm concerned, I can ask you to find t or t0, and I can give you the speed either as a percentage of the speed of light, which is nicer because do you see, the c's cancel. I could give you the speed in meters per second. That just means you have to put the speed of light in meters per second. 3 times 10 to the 8th meters per second. More typing. Example 7. What's example 7 asking me to find? V. I used to make the kids get the V by itself, but it's pretty complicated. And so 2 years ago, I decided to start having mercy. On the back of your green sheet, is there a V equals equation that has T's and T zeros in it?
Yeah.
So V equals question mark. I see 20 years. That 20, is that T or T0?
T.
How do you know? Okay. What's that 10? Which equation? Square root of 1 minus, I can never remember whether the T0 or the T is on top. Which one's on the top?
T0 on the top.
T0 over T all squared. And T squared over T squared is the same as all squared. Mr. Dewick, I'm noticing some patterns and some repetitions in these equations. Yes. Mr. Dewick, is there a shorter way to write some of it? Yes. We'll get to that next lesson. Okay. Yeah. Are you still stretching? Leave the C right there for a second, please. Don't type in 3 times 10 to the 8th. But do type in square root of 1 minus 10 over 20 all squared. And let's evaluate that square root thingy. So, again, if you have a fancy schmancy calculator, you can probably go shorter, but I would go 10 divided by 20 equals squared 1 minus that square root of that. Oh, typo. Do you get 0.86602? Yeah? So look up. Are you saying you got this? 0.866? See? Isn't that 86.6% of the speed of light? Right?
Yeah.
That's one a lot of nerds have memorized. If you want time to move twice as fast on the Earth as back home, if you go 86.6% of the speed of light, that'll do it. What if I wanted this as an actual number? So this would be as a percentage. What if I wanted this in meters per second? In meters per second, V equals 0.866 times 3 times 10 to the 8th. Except use your answer button. So answer button times 3 times 10 to the 8th. In meters per second, it's 2.598. That's a good place to round off, is probably after the 8 because there's a 0 there. 2.598 times 10 to the 8th. We cannot get spaceships to go this fast, but in the Large Hadron Collider, we're getting protons and particles to go far faster than this. A couple more, we're done, yeah? Yeah. Example 8. By how much is time expanded, dilated, from a fixed observer's point of view if a spaceship is moving at 1/2 of the speed of light? What's this question asking me to find?
T0 minus T0 minus T. That's T.
It's asking me to find T. Did they give me time on board the spaceship? And the reason is here, they're just asking for how much it's expanded by. 1 second, 1 year, 1 minute, 1 day, 1 hour. I don't care. I'll let t0. I just want to know what happens to one of these time units on the spaceship, and then I can compare that to what happens to a single time unit on the Earth. Speed is 0.5 c. So if you're going half the speed of light, how noticeable is this? Is this asking me to find t or t0? So t is going to be t0 divided by the square root thingy, yes? One divided by the square root of 1 minus 0.5 c over c all squared. Do you see? Do you see? Do you see? What do you see? C's cancel. Try typing this one in on your own just to see if you can do this one on your own. Oh, sorry, no units. You get 1.15? So for every second on the spaceship, 1.15 seconds back home on Earth. Or for every hour on the spaceship, 1.15 hours back home on the Earth. Or for every year on the spaceship. So traveling at half the speed of light, noticeable, but nowhere near as dramatic as some of the other examples that I was making up. But noticeable. Let's go faster. What about 80% of the speed of light? Well, here, again, we want to find time back on Earth. It's going to be t0 all over the square root of 1 minus v over c all squared. And again, how do I know they want me to find time back on Earth? Fixed observer. That's Earth. Again, Annika, because they didn't give me a time, I just assume, let's put a 1 in for on the spaceship, and let's see how one time unit on the spaceship compares to a time unit back home on Earth. Do you see? Do you see? Do you see? If I was typing this in one fell swoop, I would go 1 over, and then I'd probably have to hit a bracket, or I can put a bracket inside the square root. 1 minus 0.8 squared, close off the square root. Do you get 1.6 repeating? 1.67? So every second on Earth, every second on the spaceship, 1.67 seconds goes by on the Earth. We would say that this has a time dilation factor of 67% or something like that. But whatever. Important note. For now, we are assuming A equals 0. Einstein at this point did not know how to work acceleration into his equations. In fact, the theory of special relativity should be called the theory of special case relativity. And what's the special case? A equals 0. The math to prove general relativity took Einstein 10 years. And it allowed him to include acceleration. Oh, and it also allowed him to explain gravity, because gravity is a form of acceleration. Yep. Case. Special case relativity. C-A-C-E. C-A-S-E. C-E. C-A-S-E. What's your homework? Try every question. Probably need to do these on a separate piece of paper. Okay?